There are situations where you need to make sure concurrent processes that could potentially be changing the same record don't cause data inconsistencies. Let's take a look at one example. In this system, I have a naive and contrived implementation of a banking system. We have accounts with balance. Let's say we have two processes changing this account's balance. The first one wants to add $25, and the second one wants to withdraw $10. Given that the account has $50 in balance, the end result should be $65. We are going to simulate this with two IRB sessions connecting to the same database. The first process loads the account. Then the second process loads it as well. Now the first one changes the balance. At this point, the second process has already loaded the account in memory. As you can see, it still has $50 in balance. If it proceeds and withdraws $10 from the account, here's what happens. As you can see, the balance is now $40 instead of the $65 we expected, because the second process saved for last. The moment the first process saved the record, the balance in the database was $75, but the second process had already loaded the account with $50 in balance. Its in-memory account became stale, which means it didn't have the most up-to-date information anymore. Then it changed the balance to $40 and saved that, ignoring the change from the first process. To solve this, we need to prevent processes from working with stale data. Some sort of locking is usually the solution for this. We can lock the record to prevent concurrent updates. Active Record provides two kinds of locking, pessimistic and optimistic. Pessimistic locking uses database locks to prevent simultaneous access to a specific table row. Optimistic locking uses a database field to control the record version, preventing a process from updating a stale object. In this episode, I'll explain how pessimistic locking works, and I will cover optimistic locking in the next one. Let's change our code to grab a database lock on the record we are trying to update. First, we need to restart our exercise with a $50 account. Let's load it in the first process and in the second. Now when making changes, we'll call withLock like this. As you can see, the withLock call created a transaction and reloaded the account. You can see there's a select statement in there pulling the account from the database again, even though it was already in memory. You can also notice there's a for update modifier at the end of the select statement. That's how you lock a record in Postgres, which is the database I'm using, and Active Record abstracts this for us. Until this transaction is committed or rolled back, that particular account cannot be selected for update by another transaction. This prevents concurrent access to the account. Then, the rest of the statements are straightforward. We update the account and commit the transaction. At this point, we know the second process has stale data in memory. As you can see, its balance is still $50. So let's run its update again, but using withLock. As you can see, the account was again reloaded from the database right after starting the transaction. The for update modifier is here again to tell the database to lock this record so no other transaction can lock it. This guarantees both processes are working with an up-to-date object. We can confirm the balance is correct now by reloading the account. If both processes run at the same time, the database will only allow one of them to access the record at a time. To see that, let's restart the exercise and this time make the first process sleep for a while before returning so we have time to kick off the second one. And in the second process, let's run the update without sleeping. As you can see, the second process is frozen until the first one commits its transaction, releasing the lock. This may be a good enough solution for some scenarios, but it has some downsides. First, you do have to remember to call withLock everywhere you intend to update the account's balance. This account update is straightforward, but you might have scenarios in which you would, for example, only conditionally update the record, and in that case, you might end up unnecessarily locking the record. This solution also has scalability issues. You might hold a record locked for longer than you need if you do more work within the transaction. If you have high traffic, you'll get database lock contention if many requests try to grab a lock to update the same record. One process will execute at a time, the others will be kept waiting. You can easily get deadlocks if you have transactions competing for the same resources. In the next episode, I'll show you a better locking solution that's also built into Active Record and scales a lot better. Thank you for watching, and I hope you enjoyed this snack.